Hello everyone, thank you for coming to this presentation. Today I'm going to talk about the studies we have done for the recent Sparta earthquake. This earthquake occurred roughly 2 months ago near Sparta in North Carolina. The depth of this earthquake is quite shallow. It's the largest one in this area in the past 100 years. Also, interestingly, prior to the main shock, there is a group of foreshocks. Motivated by this uniqueness of this earthquake, this study aims to take a careful look of the whole sequence, which will help us to better understand the seismogenic process in this intraplate regime. To do so, we first need a complete earthquake catalog. We put together various detection methods and tools to make a high-quality catalog, and here is the workflow. It can be roughly divided to 3 stages. In the first stage, we use a deep learning phase picker, EQ transformer, to pick PNS waves automatically from continuous data, and then we locate them using hypoinverse given a local 1D velocity model. In stage 2, we compare this deep learning catalog with the standard USGS catalog and combine these two. In stage 3, we use the earthquakes in this combined catalog as templates and perform a match filter to detect more earthquakes. After measure the magnitudes and doing relocation, we acquire a final catalog. Let's take a look at some examples for each stage. In first stage, we use the deep learning model to pick PNS waves from continuous waveforms. The study period is roughly a month from August 6th to September 3rd. We use 28 stations surrounding the main shock in the first 10 days, and then we switch to a subnetwork of 10 stations near the study area. The locations of the 10 stations are shown below. Here on the right, you can see an example of an earthquake picked by the deep learning picker. The blue and the purple lines mark the PNS arrivals. Using deep learning, we were able to identify 59 more earthquakes that were now listed in the USGS catalog. This is equal to a 30% increased number of earthquakes. Here on the right figure shows you the locations of the earthquakes, with the red dots mark the newly detected events. You can see that the new events fill in some gaps on the map. With this catalog, we then use match filter to detect more events. For each earthquake, we cut a waveform around the PNS arrival and then cross-correlate them with continuous data to pick up similar events. The right figure shows an example of a new aftershocks that's detected by this method. The waveform in red color is the templates, and the waveform in the black color is the detections. You can see that they are very similar to each other. After using matched filter to detect all the new events possible in a 1-month period, we use a relocation program as Colloc to relocate the earthquakes. This algorithm takes in the differential time and cross correlations of earthquakes, and then relocate all the event clusters in the catalog to get precise relative locations. Here on the right shows you the final locations of the template earthquakes, as well as detected events picked up by match filter. As you can see, we identified 139 more events, and the earthquake starts to show some linearities. We will circle back to the spatial distribution of earthquakes in a few slides. We measure the magnitudes of the earthquakes in this new catalog, follow the methods in Shelley et al. 2016 paper. So for the template events with magnitudes determined, we extract the relationship of their magnitude ratio and their magnitude differences. And use this relationship, we were able to determine the magnitudes of the earthquakes in the new catalog. The magnitude distribution here suggests that we were able to detect a more smaller events with magnitude below -1 compared to the original earthquake catalog. Here is the magnitude distribution with time. X-axis shows the day relative to the main shock. As you can see, in the first few days, we only detected events with magnitude larger than 0. This is likely due to the lack of local stations. And after the local temporary stations were deployed, we were able to detect more smaller events. Most of the aftershocks are in the range of magnitude between 0.2 to -2. We also see the magnitude decays with time after the main event. Um, the largest aftershock directly drops to magnitude 3, and there's no magnitude 4 events. This could be due to the big stress drop of the main shock, and the remaining stress is not enough to produce magnitude 4 events. The right figure here shows the daily seismicity rate. We, on average, get 14 events per day in the first month, though, again, a lot of the seismicity were missing in the earlier days. Now let's come back to the spatial distribution of the earthquakes. Here is the density distribution of the earthquakes in our new catalog. You can see the density plot highlights two clusters, one in the north and one in the south. The main shock is located on the northern edge of the southern cluster, and the southern cluster seems to extend in the northeast-southwest direction. If we connect the two centers of the cluster, the direction is roughly aligned with the fault plane, striking 299 degrees from the USGS focal mechanism solution. These two clusters can also be seen on the vertical profile. As you can see, the separation of two clusters is roughly coincident with the topographic low on the surface. Here we compare the surface structure with earthquake locations. In the large scale, the local structures are parallelly trending northeast-southwest, which is not aligned with either of the fault planes as the focal mechanism suggests. In a more zoom-in plot, we can see that these two clusters are separated at where a river is, and the spatial extension of the southern clusters is trending northeast-southwest, which is aligned with the local structure. There is a possibility that after the main shock, some local structures, old structures trending this direction were reactivated, which caused the seismicity to be distributed along this direction. But we need to do more studies to confirm that. Here is the depth evolution of the earthquakes with respect to time. As you can see, in the earlier days, we see more deeper events, and roughly after 4 days, the seismicities became shallower, and they are concentrated at depths between 0 to 4. This could be real, but it can also be due to the lack of local stations in the earlier days. One thing I want to point out is that after relocation, our main shock was pushed to 5.6 kilometer depths, which is in between the two depths reported on the USGS website. Those two depths are 7.6 and 3.0. Here is a closer look of the foreshock sequence. Each of the colored dots is a foreshock. The color indicates the day relative to the main shock. We noticed that the foreshock's locations seem to change with time. It started out at the deeper depths further away from the main shock, and then it became shallower and closer to the main shock. You can also see this pattern on a different view on the right, where the x-axis is time relative to the main shock, and y-axis is the depth. Again, this depth evolution of foreshocks can be real, but we also want to point out that, again, in the earlier days, due to the lack of local stations, the depth uncertainty of those foreshocks can be high. Here is a preliminary plot of a way we would like to do in order to put more constraints on the foreshock locations. Here are the waveforms of 9 foreshocks recorded at one single station. T1 marks the P arrivals. On the right figure shows the cross-correlation coefficient metrics of each of the event pairs. From the S-B time and the cross-correlation coefficients, you can see that some foreshocks may be closer than what the catalog suggests. Some of them may actually be be located within a 2 to 5 kilometers range. In the future, we will take a closer look at the foreshock sequence and perform more sophisticated analysis to see what these foreshocks can tell us about the seismic behaviors in this area. To summarize, we came up with a workflow to combine deep learning, match filter, and other techniques to create a high-quality earthquake catalog in a 1 month's time span. This catalog contains 2 times of earthquakes as of the standard catalog. We were able to detect more small events with magnitudes below -1 in the density distribution suggests there are 2 clusters, with main shock on the edge of the southern cluster. The connection of 2 clusters align with the 299-degree fault plan from the USGS focal mechanism solution. However, the southern cluster extends in the northeast-southwest direction, which is consistent with the local structure. We detected 15 foreshocks preceding the main shock, and the actual locations of them may be more confined in space. Thank you for your listening. Looking forward to your questions.